Welcome back. In today's pencast, we're going to go over Dirac notation. This is a super cool notation that all physicists use when they're doing quantum mechanics calculations. I hope you are very excited for today's pencast. Recall that wave functions are actually just vectors. Even though you've been looking at it and doing a lot of calculus with these wave functions, in reality, we can actually picture them as vectors. And the way that that comes up is that for any psi of x, we can actually write it as a linear combination of coefficients times an orthonormal set of functions. Mathematically, we've written that down here as the sum over I of ci times phi I of x. And what this allows us to do is this allows us to represent this wave function psi of x as just a list of these coefficients, c1, c2, cn, maybe you have infinitely many of these. And this representation is now just like a vector that you've seen in linear algebra. And this fundamentally is how physicists think about wave functions as vectors. Dirac notation is notation for vectors. And it's made up of two important ingredients. One is the ket, and for any wave function psi of x, we'll just draw a vertical bar to its left and a right angle bracket to its right, and call that a ket. This just means that we're thinking about psi of x as a vector. The other important ingredient is the bra. For psi star of x, we can actually write that as a left angle bracket, psi of x, and then a right vertical line. These two come together to create norms or inner products of different wave functions. Notice that we've written the bra psi of x next to the ket psi of x, sharing that vertical line. This is the notation for an inner product. It's also called a bracket or bracket, spelled incorrectly. That's on purpose. And this, of course, is just equal to the integral of psi star of x times psi of x. And we all know this integral. This is just equal to 1 because psi of x is a normalized wave function. It's a proper wave function. And this is actually the meat of Dirac notation, but there's a few details we should go over. The first one is in regard to abbreviations. And abbreviations are often used instead of writing the whole wave function in between those angle brackets and vertical lines. For momentum eigenfunctions, for example, I could write the whole eigenfunction in between the vertical line and, in this case, the right angle bracket to represent the ket. But instead, most people would just write the letter p inside of a vertical line and a right angle bracket, and people would understand that this is actually just the same thing, and this is actually just the momentum eigenfunction with eigenvalue p. This turns out to be a very powerful tool. You could actually name your vectors anything you want. You can name your vectors, I don't know, the banana vector, if you really wanted. But remember, with great power comes great responsibility. Name them well. And remember, everything that goes in between that vertical line and the left or right angle bracket is just a label, so you know exactly which wave function or which vector you're representing. As an example, let's now take a sandwich, or let's take an inner product between p and psi of x comma t. Notice I snuck in this t dependence, the time dependence, into psi of x comma t, and that's totally fine. That's also a vector. We can take this inner product. That means we take the integral of the eigenfunction times psi of x comma t, and this is just the momentum space representation of psi of x, c of p comma t, which we've seen a few sections ago. So this is super awesome. Abbreviations are great. Physicists use them all the time, and look out for them in this course. The last thing that is super important with Dirac notation is operator sandwiches. What that is we can take any inner product between any two wave functions, between any two bra and kets, and we can stick an operator in between. We've written that here as the left angle bracket, phi of x, vertical line, the operator a, and then another vertical line, psi of x, and a right angle bracket. As you may guess, all this is similarly that integral that we talked about before, but with the a snuck in between the phi star of x and the psi of x. This is called an operator sandwich in the sense that a is kind of like the filling in the sandwich, where we have one side is phi of x and one side is psi of x in this case. This is actually the terminology that's used. I didn't use it. As an example, let's consider the inner product between psi of x with the momentum operator snuck in between another psi of x. Of course, this is just the integral of psi star of x times the p operator applied to psi of x. And this, of course, is just the expectation value of the p operator. This is a very general situation in which if you have the same wave function in the bra and the ket, and the operator in between, you actually are evaluating the expectation of that operator, which is what we see here with p. Today, we talked about Dirac notation, this super cool notation for, as we learned, doing linear algebra. Wave functions are just vectors, and we can combine them to create inner products, just numbers. Two important details about Dirac notation are the fact that abbreviations are used everywhere in physics to represent wave functions and those vectors, and also operator sandwiches are used constantly throughout quantum mechanics calculations. In our particular case, we looked at the expectation value of the p operator, which was just the p operator snuck in between a bra and a ket of psi of x.